So this is inverse trigonometry, hot sums, which are higher order thinking sums. The 2 by 3 into tan inverse of 3ab square minus a cube by b cube minus 3a square b plus a 2 by 3 a tan inverse of a 3xy square minus x cube by y cube minus 3x square y. And this is the question. You have to prove this to be equal to tan inverse of 2 alpha beta by alpha square minus beta square. It's also given in the question that alpha can be taken as by minus ax and beta can be taken as bx plus ay. So let's prove this sum. Let's prove that question. And so then when I look at this, can you see a 3 here and a 3 here? It seems like a 3 tan theta minus tan cube theta by 1 minus 3 tan square theta. It has got a resemblance of a tan 3 theta formula. Moreover, we need it as tan inverse of tan. So we need it as tan inverse of tan 3 theta. So that makes it easier, and so you can therefore guess it that somehow you're going to make it into form 3 tan theta minus tan cube theta by 1 minus 3 tan square theta. The fact that the b cube has to become 1 so that this whole thing can become a tan 3 theta, and when you get in the tan inverse and tan get cancelled, and when you get to the 2 by 3, the 3 and 3 get cancelled, it merely becomes a 2 theta. Okay, so then with that in mind, since I need 1 in this place, I'm deciding I'm going to divide throughout by a b cube, and for this term, for the second term, I'm going to divide throughout by a y cube. So dividing throughout by b cube, you get 2 by 3 into tan inverse of 3a by b minus a cube by b cube by 1 minus 3a square by b square plus 2 by 3 into tan inverse of dividing throughout by y cube on the right side, y is y cube, tan inverse of 3x by y minus x cube by y cube by 1 minus 3x square by y square, dividing each and every term by y cube on this side and by x cube by b cube on this side. Okay, so you get this like this. So you understood how do I get that hint. Okay, now you're gonna consider it's like 3 tan theta minus tan cube theta now, and this is also same. So a by b can be considered as tan a instead of tan theta, because x by y and a by b, there are two things that I have. There's an a by b and there's an x by y. So for convenience, I'm going to assume tan a is equal to a by b. A is tan inverse of a by b. And here tan b is equal to x by y. B is tan inverse of x by y. So that this can become 2 by 3 tan inverse of 3 tan theta minus tan cube theta. From here we are substituting by 1 minus 3 tan square theta, which is actually a because we assumed it as tan a, plus 2 by 3 into tan inverse of 3 tan b minus tan cube b by 1 minus 3 tan square b. So this is 2 by 3 into tan inverse of tan 3a, and similarly this is 2 by 3 into tan inverse of tan 3b. So now the 3 and the 3 get cancelled, the 3 and the 3 get cancelled, you get 2a plus 2b, which is 2 into a plus b. What is a from here and what is b from here? It's 2 into tan inverse of a by b plus tan inverse of x by y. So therefore, hope it's recording. Yeah. So therefore, it's like tan inverse of x plus tan inverse of y again, where this itself is like x and this is like a y. Okay. So undo this. So let's write 2 into tan inverse of x plus y by 1 minus xy, that's a formula, a by b plus x by y by 1 minus a by b into x by y. Okay, so the next step is to take LCM. When you take LCM for this, it's 2 into tan inverse of, it's by is the LCM. So it's ay plus bx. Leave the denominator off because both the denominators, the numerator's denominator is also by, the denominator's denominator is also by, and by get cancelled. So you get by minus ax. So this is what you get. And already the question, it's been given that this is alpha and this is beta, by minus ax and bx plus ay. And substituting back in here, this is 2 into tan inverse of beta by alpha. This is 2 tan inverse formula. A 2 tan inverse of x is tan inverse of 2x by 1 minus x square, where in the place of x you have beta by alpha. So it's tan inverse of 2 beta by alpha by 1 minus beta square by alpha square. So when again taking an LCM, it's 2 alpha beta by alpha square minus beta square. Just try to take calculated tan inverse of 2 beta by alpha square minus beta square by alpha, where this alpha square and this alpha get cancelled, and so this goes up. I hope you understood. So that's what it is, and this is what you need to prove, and that's the question. To prove that was the question itself, that this is the right hand side that you needed and you got it. So let's go next question that we discussed in higher order thinking sums. The next question was a cos inverse of cos alpha plus cos beta by 1 plus cos alpha cos beta is equal to 2 into tan inverse of tan alpha by 2 tan beta by 2. The moment you see this is prove that sum, okay? So I prefer to solve from the right hand side because you already have a 2 here, 2 tan inverse of x. This whole thing is like x. And so tan inverse of 2x by 1 minus x square. So this is going to become right hand side, tan inverse of 2x by 1 minus x square, because this whole thing becomes an x, 2 tan inverse of x. Okay, so then next step. So then now I'm going to write it as 2 tan alpha by 2. No, the best thing is to write it as not tan inverse. You can just write directly as cos inverse because you have a direct relation. So isn't that better? Because you want the answer in terms of cos inverse. A 2 tan inverse of x in terms of cos inverse is 1 minus x square by 1 plus x square. So ideally you should use this formula to get this directly. So I'm going to write a cos inverse of 1 minus x square, a tan square alpha by 2, tan square beta by 2 by 1 plus a tan square alpha by 2 into tan square beta by 2. Now we can write tan as sin square alpha by 2 by cos square alpha by 2, a sin square beta by 2 by a cos square beta by 2 by a 1 plus a sin square alpha by 2 by a cos square alpha by 2 and a sin square beta by 2 by a cos square beta by 2. So now it's cos inverse, and we take LCM, we get it as cos square alpha by 2 cos square beta by 2 minus sin square alpha by 2 into sin square beta by 2 by, let's cancel off the denominators of the numerator and the denominator of the denominator, which is both cos square alpha by 2 cos square beta by 2. So let's take an LCM here also. So you get cos square alpha by 2 cos square beta by 2 plus sin square alpha by 2 into sin square beta by 2. This is where children will struggle. They won't know how to solve this. You have to multiply it with 2 cos square alpha by 2, 2 cos square beta by 2. minus 2 sine square alpha by 2, 2 sine square beta by 2, by everywhere with the 2 cos square alpha by 2, 2 cos square beta by 2, plus 2 sine square alpha by 2, 2 sine square beta by 2. Because 1 plus cos alpha is 2 cos square alpha by 2. 1 plus cos beta is 2 cos square beta by 2. 1 minus cos alpha is 2 sin square beta alpha by 2. 1 minus cos beta is 2 sin square beta by 2. The advantage is this, and this is something very difficult to remember. So it's 1 plus cos alpha into 1 plus cos beta minus 1 minus cos alpha into 1 minus cos beta by a 1 plus cos alpha into 1 plus cos beta plus 1 minus cos alpha into 1 minus cos beta. Next step is to take everything inside. Just multiply them inside and see what you're getting. It's cos inverse of 1 plus cos beta plus cos alpha plus cos alpha cos beta. Similarly, you can take the right hand side also and multiply them inside. It's 1 minus cos alpha minus cos beta plus cos alpha cos beta. Similarly, denominator also, it's going to be the same as this, right? Just can copy the same thing. 1 plus cos beta plus cos alpha cos beta plus, and same thing, 1 minus cos alpha minus cos beta plus cos alpha cos beta. Now open the bracket. Cos inverse of 1 plus cos beta plus cos alpha cos beta minus 1 plus cos alpha plus cos beta minus cos alpha cos beta. So if you see, the cos alpha cos beta is getting cancelled, the 1 and minus 1 is getting cancelled by, open the bracket in the denominator also, cos beta plus cos alpha cos beta plus 1 minus cos alpha minus cos beta plus cos alpha cos beta. In this, the cos beta is getting cancelled, cos alpha is getting cancelled. Okay, so what are you left with? A cos inverse of a 2 cos alpha plus a 2 cos beta by a 2 plus 2 cos alpha cos beta, which is nothing but 2 can be taken out common. You have a cos alpha plus cos beta by 1 plus cos alpha cos beta, and that's exactly what's your right hand side or left hand side in this case. So don't convert a 2 tan inverse in terms of 1 tan inverse, because you need it as cos inverse. So straight away use this formula and do it. Okay, so you got the answer. Let's go to the next question. The next question is the third question, which is in the hot sums. Y is equal to cot inverse of root cos x minus tan inverse of root cos x. Prove that sin y is equal to tan square x by 2. The moment you see this, this is what you need to prove from what is given is this. So write one of the cot inverse. If it was a plus, I could have written pi by 2 because identity. It's not a plus, it's with a minus. So write it as pi by 2 minus tan inverse of root cos x minus this cot inverse I'm writing with identity, and a tan inverse of root cos x. So pi by 2 minus 2 tan inverse of root cos x, and this is like a 2 tan inverse of x, where root cos x is behaving like x. Okay, so you're going to convert into 1 tan inverse, or can I write it as 1 sine inverse directly? Yeah, that's even appropriate because I have something called a sine here. So I know 2 tan inverse of x can be written as sine inverse of 2x by 1 plus x square, but in the place of x you have root cos x, so this will become sine inverse of 2 root cos x by 1 plus cos x. So ideally, because of the sine y, I would like to convert the 2 tan inverse in terms of sine inverse. So it becomes sine inverse of 2 root cos x by 1 plus cos x. Now This is like pi by 2 minus sine inverse, which will become cos inverse identity. 2, this is again like an x. Pi by 2 minus sine inverse of x is cos inverse of 2 root cos x by 1 plus cos x. So it has become pi by 2 minus sine inverse has become cos inverse using identity in inverse trigonometry, which is equal to y. And take this to the other side, you get cos y is 2 root cos x by 1 plus cos x. The beauty is you want a sin y. Can you see, prove that you want a sin y. And you already got a cos y, and you know by identities, you know cos y is root of 1 minus sin square y. So you can write 2 into root cos x by 1 plus cos x, and now you can square both sides. 1 minus sin square y is 4 cos x by 1 plus cos x the whole square. Take this to this side and sin square to the other side. 1 minus 4 cos x by 1 plus cos x the whole square is equal to sin square y. Now take LCM. It will be 1 plus 2 cos x plus cos square x minus 4 cos x by 1 plus cos x the whole square is equal to sin square y. Now this and this is solvable. It's plus 2 cos x minus 4 cos x is 1 minus 2 cos x plus cos square x by 1 plus cos x the whole square is equal to sin square y. And this itself is like 1 minus cos x the whole square by 1 plus cos x the whole square is equal to sin square y. Therefore, a sin y itself is 1 minus cos x by 1 plus cos x, whose formula this is directly tan square x by 2. How do you get that? A 1 minus cos x is 2 sin square x by 2. 1 plus cos x is 2 cos square x by 2. 2 and 2 get cancelled. A sin y itself is therefore a sin y itself is tan square x by 2. That's all. Okay. So that's about the sum, and that's what we need to prove. So let's go to next question. Next question is this, which is the fourth sum, which there is a prove that a summation of m is equal to 1 to n, a tan inverse of 2m by m to the power 4 plus m square plus 2 is equal to tan inverse of n square plus n by n square plus n plus 2. You have to prove this. Okay, so what do you do? There is a manipulation format. This is a manipulation format. How do I understand that there's a manipulation? I see m to the power 4. I see a 2. So I'm just thinking, can I write it as 2m as m plus m? And then add m square, and then subtract m square, and then you have a 2 here, which means I can add a plus 1 and I can subtract a minus 1, and then write it as m to the power 4 plus m square plus 2 with a tan inverse. This kind of manipulation is important for doing calculus in a later stage, so now itself you can learn it. So writing the 2m as m plus m, and then adding an m square, subtracting an m square, adding a plus 1 and subtracting m square. And this one, next step is like tan inverse of m square plus m plus 1, which is going to act as an x, minus m square minus m plus 1, which is going to act as a y, which is like tan inverse of x minus y by, I should get a 1 plus xy. So write it as 1 plus xy, which is x and which is y. Just substitute, this is x and this is y. Just substitute it here. So then now try to solve the denominator, or no need. This itself is like a tan inverse of x minus tan inverse of y by 1, tan inverse of x minus tan inverse of y. Tan inverse of x minus y by 1 plus xy. You remember this formula? So then therefore I would just write it as tan inverse of x minus tan inverse of y. You multiply this, you solve this, you'll get it automatically. So then therefore it's tan inverse of x minus tan inverse of y. This tan inverse of x minus tan inverse of y. So we're trying to write it like this. Okay, so tan inverse of x is m square plus m plus 1 minus tan inverse of y is m square minus n plus 1. I write it like this. So I get it in this format. Whereas now I forgot the summation. There was a summation m is equal to 1 to n. Every term had a summation m is equal to 1 to n. M is equal to 1 to n. So basically, for this term and this term separately, you're going to use a summation. There's a summation of m is equal to 1 to n tan inverse of m square plus m plus 1 minus summation of m is equal to 1 to n a tan inverse of m square minus m plus 1, in which a summation simply means you're going to substitute 1, 2, 3, all these values. When you substitute 1, m is equal to 1. It will become, in this left hand side, it will become 1 plus 1 plus 1, which is 3, and so it will become tan inverse of 3. When you put m is equal to 2, it's 4 plus 2 plus 1, which is 7, so it's going to become tan inverse of 7. So let's put m is equal to 3. It's 9 plus 3 plus 1, which is 13, so tan inverse of 13. When you put m is equal to 4, you get 16 plus 4 plus 1 is equal to 21, which is tan inverse of 21. And basically, and goes on till m is equal to n, where it will become n square plus n plus 1 with a tan inverse of, therefore it's tan inverse of n square plus n plus 1. And all these values you're supposed to add with a dot dot dot. It goes on like that. So therefore, left hand side is tan inverse of 3 plus tan inverse of 7 plus tan inverse of 13 plus tan inverse of 21 plus dot 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 tan inverse of n square plus n plus 1. Let's do this, the second term, not left hand side, this term, and now let's solve this. Putting m, for this, putting m is equal to 1, you get 1 minus 1 plus 1, which is 1, which is actually tan inverse of 1. Putting m is equal to 2, it is 4 minus 2 plus 1, which is 3, which is tan inverse of 3. Then m is equal to 3 is 9 minus 3 plus 1, which is 7, so tan inverse of 7. Like that dot dot dot, you can put m is equal to n, and you get n square minus mn plus 1, which can be written in tan inverse of n square minus n plus 1. Substituting that with this subtraction sign brought down and opening a bracket. So this is separate and that is separate. You have a tan inverse of 1 plus tan inverse of 3 plus tan inverse of 7 plus dot 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 tan inverse of n square minus n plus 1. Now open the bracket. You get tan inverse of 3 plus tan inverse of 7 plus tan inverse of 13 plus dot 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 tan inverse of n square plus n plus 1 minus tan inverse of 1 minus tan inverse of 3 minus tan inverse of 7 minus tan inverse of n square minus n plus 1. Now you look at this, tan inverse of 3, tan inverse of 3, tan inverse of 7, tan inverse of 7. And like that it's getting cancelled. If you see, the tan inverse of 1 didn't get cancelled. And similarly, in this will not get cancelled. This is the plus. Because you see 3 and 3 is getting cancelled, 7 and 7 is getting cancelled. The first term wasn't getting cancelled. Okay. The first term in this and the last term in the first series is not getting cancelled. The first term in the first series and the last term in this first series. Okay, I hope you understood. So let's write this. What is not getting cancelled is tan inverse of n square plus n plus 1 minus tan inverse of 1. That's recording. This is again like a tan inverse of x minus tan inverse of y. So just solve it. It's tan inverse of x plus y, n square plus n plus 1, x minus y by 1 plus xy, n square plus n plus 1 into 1. Okay, so then when you open the bracket, okay, this plus 1 minus 1 get cancelled. When you open this bracket, you get tan inverse of n square plus n by n square plus n plus 1 plus 1 is 2. So this is what you get. And is that what they are asking you to prove? Yeah, that's exactly what you need on the right hand side. Without even thinking about the right hand side, we can do the sum and yet you get the answer. So let's go to next question. So there's a manipulation involved in the sum. That's the fourth sum. Let's go to fifth question. The fifth question is a summation of x is equal to 0 to n tan inverse of 1 plus x square. And you have to just solve this. That's all. It's just a question of solving it. So how to solve this? This also is manipulation. Whenever there is a summation, we're thinking of manipulation because I have to convert into tan inverse of x minus y by 1 plus xy format. So what I'll do in this question, I'll add x and subtract x. So this is like x and this is like y, and a 1 plus x into y. If I take this and multiply, I'll get it exactly like this. So therefore this is like tan inverse of x minus tan inverse of y. So this is tan inverse of 1 plus x minus tan inverse of x. But there is a summation of x is equal to 0 to n, and here also there is a summation of x is equal to 0 to n. So let's apply this, and so putting n is x is equal to 0, you get first term to be tan inverse of 1. X is equal to 1, you get tan inverse of 2. X is equal to 2, you get tan inverse of 3, and x is equal to n, you get tan inverse of 1 plus n. In this term, in this again, this is for this. In this you put x is equal to 0, you get x is equal to 0, you get tan inverse of 0. X is equal to 1, you get tan inverse of 1. X is equal to 2, you get tan inverse of 2. And x dot 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 x is equal to n, you get tan inverse of n. So let's subtract because there's a subtraction symbol. Let's write the left hand answer, tan inverse of first term's answer, tan inverse of 1 plus tan inverse of 2 plus tan inverse of 3 plus dot 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 tan inverse of 1 plus n minus of tan inverse of 0 plus tan inverse of 1 plus tan inverse of 2 plus dot 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 tan inverse of n. I'm going to open the bracket, get tan inverse of 1 plus tan inverse of 2 plus tan inverse of 3, a tan inverse of 1 plus n minus a tan inverse of 0 minus tan inverse of 1 minus tan inverse of 2 minus tan inverse of n. In this, if you see, the tan inverse of 1 is getting cancelled. This is not getting it. The first term in the second series and the last term in the first series is not getting cancelled. Rest of it is all getting cancelled. I hope you understand. So therefore this is like a tan inverse of 1 plus n minus tan inverse of 0. You all know tan inverse of 0. When will tan be 0 in inverse trigonometry? In 0. So you don't have to do tan inverse of x minus tan inverse of y. It's unnecessary because we know very clearly and directly that tan inverse of 0 is 0. Therefore the final answer is tan inverse of 1 plus n, and that's what is the final answer. Just to simplify this, you just have to simplify the summation and you get this as answer. I hope you're clear. So let's go to next question is the sixth question. The sixth question, if cos inverse of alpha plus cos inverse of beta plus cos inverse of gamma is equal to 3 pi, they're asking you to find alpha into beta plus gamma plus beta into gamma plus alpha plus gamma into alpha plus beta. It is very simple. A pi plus pi only will be 3 pi. Therefore, I'm going to assume this cos inverse of alpha as pi, a cos inverse of beta as pi, and a cos inverse of gamma as pi. I hope you understood. So let's undo this. Okay, so then therefore I'm going to write cos inverse of alpha is pi, so alpha is cos pi, which is minus 1. A cos inverse of beta is pi, a cos pi is beta, and that is also minus 1. A cos inverse of gamma is pi, a cos pi is gamma, and that's also minus 1. So you got alpha to be minus 1, beta to be minus 1, gamma to be minus 1. Just a question of substituting in this. Alpha is minus 1, beta plus gamma. minus beta, gamma plus alpha, minus gamma, plus gamma is minus 1, minus 1 alpha and beta's value. You solve this, you will get answer to be 2 plus 2 plus 2, which will be 6. So next question is the 7th sum. Prove that a tan inverse of yz by zr, no, xr, yz by xr plus tan inverse of xz by yr plus tan inverse of xy by zr is equal to pi by 2. You have to prove this to be equal to pi by 2. So let's take these two alone. It's like tan inverse of x plus tan inverse of y, which is tan inverse of x plus y by 1 minus xy. So tan inverse of x plus y by 1 minus x y, plus you still have this one which is unresolved, because we'll come back to that later. Let's take LCM. LCM is xr, yr anyway is getting cancelled. So tan inverse of, when you take, okay, let me take an LCM. For the numerator is xyr. For the denominator also it's xyr, least common multiple. There's a by here. So the numerator here will be, what is missing? An x and an r are there, y square z. A y and r are there, and so it will be x square z. And similarly, LCM is x y r square minus y z square x. So you get it like this. Now this and this is getting cancelled. A tan inverse of, what is common in the numerator? You can see the z is common. You get an x square plus y square in the numerator. By the denominator, what is common? Again an xy is common in the denominator. You get an r square minus z square. Coming back to the question, I missed out saying one thing. In this sum, they would have given one case, given that x square plus y square plus z square is equal to r square. So wherever see r square minus z square, you can write it as x square plus y square. This can be written as x square plus y square. So this is going to become tan inverse of z x square plus y square by xy into x square plus y square. So here, when you multiply this two, there should be an r square here. It is xy r square is the LCM. xy r square is the LCM. Okay, because it here already you have to multiply these two, so there will be an r square. Okay, so then you'll be left with one r here, and that r will go up, and that will make it zr. Now this and this get cancelled, so tan inverse of zr by xy, tan inverse zr by xy. Now you can bring the next term, which is an unresolved term, which is this, which is tan inverse of xy by zr. So just solve this again. It's tan inverse of x, tan inverse x plus tan inverse of y, zr by xy plus xy by zr by 1 minus zr by xy into xy by zr. Okay, and so when you solve this, you will again get, let's do LCM. The LCM for the denominator will be x, y, z, r. Whereas for this one, for the numerator, the denominator is like this. For this, it will be x, y, z, r square. So when you're taking LCM, you have an xy here, so you should multiply with xy here. What is missing is zr. So can I try writing it as z square r square, and I have a zr here, so can I write it as x square y square? I'm just trying. So here is xy z r. Oh, there's no r square here. That's just xyz r. So here I'll get xyzr minus zrxy. So you can take out, try to, this and this is getting cancelled directly. And look at this. The denominator is becoming 0. A tan inverse of infinity. And that's possible only when it's 90 degrees. So made a simple error here where it has to be r square. Just make sure you're also correcting it. So you get the answer as 90 degree. Because tan inverse of tan inverse of infinity is 90. At 90 only, tan will become infinity. So let's go to the next question. The next question is the 8th question. Sine inverse of x plus sine inverse of y plus sine inverse of z is equal to 3 pi by 2. So then they're asking me to find the value of x to the power 2006 plus y to the power 2007 plus z to the power 2008 plus 9 by x to the power 2006 plus y to the power 2007 plus z to the power 2008, whatever. And you know this is pi by 2, pi by 2, pi by 2. Then only I'll get 3 pi by 2. So assuming sine inverse of x as pi by 2, sine pi by 2 becomes an x, which is 1. Similarly, y is sine pi by 2. Similarly, sine inverse of y is pi by 2. A sine pi by 2 is what is y, which is again 1. A sine inverse of z is pi by 2. A sine pi by 2, which is z, is also 1. So you got x, y, z to be 1. Just take it and substitute that 1 here. You will get the answer. So you get 1 plus 1 plus 1 plus 9 by 3, which is a 3. So the answer will be 6. Let's go to the next question. A cot inverse of 2 square plus 1 by 2 plus cot inverse of 2 cube plus 1 by 2 square plus cot inverse of 2 to the power 4 plus 1 by 2 cube. Cot inverse of 2 square plus 1 by 2 plus cot inverse of 2 to the power 3 plus 1 by 2 square plus cot inverse of 2 to the power 4 plus 1 by 2 cube dot cot inverse of 2 to the power n plus 1 plus 1 by 2 to the power n.